Hello and welcome back. Your exam ends today, so yay. If you want to avoid the late fee, get in there before 2 p.m. I don't recommend waiting till 8 o'clock at night to get in line. Last time there were about 400 people that took the exam on Wednesday. I don't know how many have taken it already. I should have looked, but in any case, plan ahead so that you're not in a big rush towards the end of the day. One thing that I think has been floating around as a rumor that I will now confirm. I didn't mean to do this, but a student asked on Monday, are tastes and smells going to be on this exam? And I was like, didn't I ask questions on that on the last exam? I should have just said yes. But instead I said, didn't I ask about that on the last exam? And they said no, and I was like, oh. So yeah, I forgot to put that on this exam. By then I'd already written it, and so it's been out there. I hesitate to say tastes and smells will not be on this exam because I worry that that means you take that drawer in your mind that has that stuff and you just dump it out and throw it away forever. Don't do that because that stuff was kind of fun and it will show up on a future exam. So, but you don't have to worry about it for today, but you will encounter it in the future. Let's see, I think that's all that I've disclosed about the exam. 25 questions, 165 points. Should take you about the same amount of time as it took you on the previous exam. All right, so unfortunately we're in that uncomfortable part of the semester where you're getting ready for an exam, but we're already moving on. And we're going to probably finish chapter 8 today, which means that likely you're probably a little bit behind and likely you haven't done a lot on the chapter 8 study guide yet. But next time we're going to move on probably to chapter 9. So, and the pace will only continue to be relentless. And what you'll have to do from this point on is rely on the fundamentals that you've learned to deal with the large amount of detail that's coming. Okay, well, with that I want to just review a little bit. And I'm sorry, this class is a lot like drinking from a fire hose, and you want some relief, and it's coming, but it's only coming in December. And then some of you are signing up to do it again in the winter, so I don't know what to do for you there. All right. But just understand we're all doing the best we can with the limited time and energy that we have, and God loves us no matter what. All right, well, last time we were dealing with the stereochemical requirements and outcomes of the E2 reaction. And the key requirement here is that the beta proton that you remove needs to be anti to the leaving group. It needs to be anti to the leaving group so that it can engage in sigma to sigma star hyperconjugation so that the LUMO, the sigma star, can spread out onto the adjacent beta proton. So we dealt with this example, a secondary alkyl halide, and we used a molecule that is both a good nucleophile and a good base. And we were unsurprised to see the substitution product via SN2 with inversion of configuration at the stereocenter. But then we needed to consider the possible elimination reaction that would occur if this base were to remove a beta proton. Now, one of the things we saw in this starting material is there are 2 protons on the beta carbon. And if we look down the bond between the beta and the alpha carbon, we saw that in this particular conformation, when the benzene rings are anti to each other, it's HB here that is anti to the leaving group. And so it's HB that would have LUMO on it, and HB that would be reactive towards a base. When the base removes HB, electrons kick down to form a pi bond, the leaving group leaves. The 2 benzene rings that were anti to each other in this reactive conformation are trans to each other in the alkene product. And you'll notice that as the reaction proceeds, this carbon, the beta and alpha carbons, which used to be sp3 hybridized, flatten out to become sp2 hybridized. But the key thing you need to get is that the stereochemistry between these two R groups, the fact that they are trans to each other, is set by this reactive conformation. Now, remember that you can rotate around carbon-carbon sigma bonds. So even though we drew this molecule in an orientation where it was HB that could be anti to the leaving group, we need to consider the alternative conformation where HA is anti to the leaving group. And to do that, you simply start with this conformation, and then we're going to rotate HA about 120 degrees counterclockwise, so that HA is now here, HB is now here, and the R group is now here. Notice now that HA is anti to the leaving group, and the R groups, the benzene rings, are now gauche to each other rather than anti to each other. When the base removes the beta proton, pi bond forms, leaving group leaves, those two groups that were gauche to each other, as the alpha and beta carbons flatten out to become sp2 hybridized, those gauche groups will now become eclipsed with each other, and they'll end up cis to each other. So the idea here is that this reaction is what we will call stereospecific, meaning that the mechanism requires a specific stereochemical outcome. If you remove HB, anti to the leaving group, you get the trans diastereomer. If you remove HA, anti to the leaving group, you get the cis diastereomer. Okay, questions about that? Yeah? Can all E2 reactions be changed like that?
Are they all stereospecific?
E2 reaction in general is a stereospecific mechanism. As to whether all E2 reactions will have the potential for cis or trans diastereomers, that will depend on the structure of the starting material, and I'll show you some examples of that. Okay, yes?
Are you going to show both, like the cis and trans isomer
Yeah.
cases, or just the one? Like,
So,
the product?
right, if I ask you to predict the products, it would be a select all that apply situation. In this case, you would select the SN2 product and these two E2 products. Now, if I ask you which elimination product is the major product, then you fall back on something called the Zaitsev rule, which says that the more stable alkene is the major product, is the major elimination product. And the reason for that is that the transition state of the E2 reaction has a high degree of alkene character, which means that a transition state leading to a more stable alkene will itself be lower in energy and therefore faster to get over. And so the more stable product actually forms faster. And then the principle here is that trans is more stable than cis because of sterics. In the cis diastereomer, these benzene rings are bumping into each other. In the trans diastereomer, they're not. Okay. One interesting thing that is not so important now, but you'll see it at the very end of the semester, and then again, if you take the OChem Lab 353, this kind of thing will be a fairly big deal. You see that if we remove HB, we get the trans diastereomer. If we remove HA, we get the cis diastereomer. What that tells us is that HA and HB are not actually identical. If you remove them and get different products, they're not identical. And that's a new finding. You're used to looking at CH2 protons and saying, oh, those two protons are identical. The reason they're not is because of the presence of this nearby stereocenter. And that's illustrated by the fact that removing either of them gives you a different alkene product. We're going to have a word for that later on in the class. We will say, and this word it'll matter a lot in the OChem lab. Protons that, when they're removed, lead to different diastereomers are called diastereotopic. Topic meaning having to do with the shape of the molecule. So they are in two different and unique environments. Okay, so you'll need to be able to think through this both backwards and forwards. So I want to give you a slightly more challenging situation and have you deal with it from the thinking backwards perspective. So let's suppose that you want to get this alkene product where two benzene rings are cis to each other. And let's just suppose, you want exclusively the Z stereoisomer. So your task, for whatever reason, your inexplicable task is that you're supposed to make this molecule exclusively. And this is a problem because any strategy that gives you a mixture of the cis and the trans product, so I'm going to draw none of the alternative. Any alternative that gives you some of the alternative diastereomer is likely to be problematic because that E diastereomer would be more stable because the benzene rings aren't bumping into each other. So any strategy that would give you a mixture of both products, we're going to immediately disqualify. We want a strategy that gives us only the desired stereoisomer. We're going to use here a base that's a strong base but a weak nucleophile. This is tert butoxide. It's a weak nucleophile because of sterics. So we're not going to worry about the competing substitution reaction. Now, if you remember in an E2 reaction, you have a leaving group on the alpha carbon, and then you have a proton on the beta carbon. And we eliminate both the beta proton and the leaving group. And in its place, we have a pi bond between the alpha and the beta carbons. It's pretty easy to tell in our product where the pi bond is. It's difficult to know which one was the alpha carbon that had the leaving group and which one was the beta carbon that had the protons. So our task is to choose a starting material that will give us only this desired product shown here, only the Z isomer and none of the trans isomer. So we're going to work through this together, thinking backwards. And as the semester progresses, you need to be able to think backwards on reactions like this. If you know what the product is and what the reagent is, can you think backwards to what the starting material would have been? So let's consider some possibilities. And of course, I'm not going to lead with the one that works. But it'll be important to figure out why it doesn't work. All right, let's choose this possibility where we put the leaving group on the same carbon as the methyl group. And then this is our beta carbon. And we have two protons, HB and HA. So let's look down the bond between the beta and alpha carbons and let's draw a Newman projection. From our perspective here, the benzene ring, which I'll represent with an R group on the beta carbon in the front, would be coming out to our right. HB would be angled downward to our left, and HA would be angled upward to our right. And then in the back, the benzene ring, which I'm going to abbreviate with R, is going to be to our left, with the iodide leaving group coming up to our right, and then the methyl group going down to our right. So in this conformation, it's actually HB that is anti to the leaving group. So if I do the elimination reaction, what's going to be the stereochemistry in my product? What's going to be the relationship between those benzene rings? Going to be trans to each other, right? So this is going to be the product if we start with this starting material. So right away, we see that that starting material is a bad idea. Now, it is true that we could rotate around the bond between alpha and beta carbons so that HA would be anti to the leaving group. And it is true that if we remove HA while it's anti to the leaving group, that we will get the cis product. But the problem with that, is that the trans product that we made above is more favorable to form because it's more stable than the cis product we formed below. And therefore, the best we could get, if this is our starting material, is for the desired product to be a minor component of our reaction. Yes?
How do you know with the first Newman projection that it is the trans configuration?
So the first Newman projection, the R groups are anti to each other. And as the reaction progresses, and the beta carbon in the front and the alpha carbon in the back rehybridize to become sp2 hybridized in the product, this is what the product will look like from the Newman projection perspective. And the benzene rings are still on opposite sides, which is what we observe here. Yeah?
How did you get that first Newman projection? I'm just confused on how HB and I are, the leading group are anti to each other, and why it's not HA and
So starting from here,
I'm looking at it, shouldn't it be
HA is a wedge pointing out towards you, and I is also a wedge pointing out towards you. HB is a dash pointing towards the top of the page but down away from you. So if we look at it, putting our face sort of here and turning and looking at it from that perspective, looking down the bond, the benzene ring would be out to our right, HA would be up, HB would be down, and then on the carbon in the back, I is pointing up. Do you see it now? I'm sorry, I just sort of, yeah, okay. It looks, from this perspective, if you just get the fact that HA is pointing towards the top of the page and I is pointing to the bottom of the page, yeah, you could think that they are anti, but if you take into account the wedge, they're angled like this, and you need them to be like that. Okay, yes?
So the two molecules that you just drew, those
They are the same molecule. These two are not the same molecule because you can't rotate around a pi bond. These two are,
Oh,
because the
you're-
pi bond isn't formed yet.
Oh, you're rotating the sigma.
Yep.
Okay.
Yep. All right, so yes.
Is the way you're naming HA and HB, is that just a separate thing, or is there like a system for them?
There's not a system for which one I call A or B.
Okay.
Yep, good. Okay, so let's try something else. It seems like the strategy of having the I on the carbon that is more substituted, so there are two beta protons. It seems like that's a losing strategy, because as long as there are two beta protons, we're going to have two possible products. So let's try something else. Let's move the I group over to this carbon and then a proton over to the other carbon. So here's our starting material. Let's try let's have this one be the beta carbon. And let's try iodide as a dash rather than a wedge. So we'll call this HA. Here is the leaving group. And what we need to ask is HA anti to that leaving group? You'll get to the point where you'll be able to recognize without drawing the Newman projection that HA is indeed anti to the leaving group. The reason you can tell that's true here is I is pointing to the top of the page but is a dash, and HA is pointing towards the bottom of the page but is a wedge. And that's a situation where if you draw the Newman projection looking down the bond between beta and alpha carbons, what you will see, here's the R group, and HA is here, methyl is here, here's the other benzene ring, proton is there, iodide is there. HA is anti to the leaving group. Unfortunately, we chose a starting material such that when HA is anti to the leaving group, there's that pesky trans product again, right? Where the R groups are opposite each other, and that is, of course, the undesired product. So we just made things worse because we got 100% of the undesired product, whereas the option above at least gave us the major undesired product and then a small amount, a minor amount of the desired product. So, okay, good. We got one and only one product. We just got the wrong one. So, any strategies for making this better? Anything I could change? Yeah?
I just have a question. Why is you said that trans is desired, like lower energy. Why is the cis example, or in this example, it's trans right now, but you said it's undesired?
So, right. There's a difference between being the desired versus undesired product and being major or minor. The desired versus undesired product is an arbitrary thing. I made that up in this problem. I said, I want the cis isomer. Yeah. You're right that the cis isomer is less stable than the trans isomer, but we need a strategy for getting it. Go ahead.
You just switch the stereochemistry around the alpha or beta carbon.
So yeah, you could switch the stereochemistry of the alpha or the beta carbon, but not both, right? So let's just choose, let's keep the beta carbon the same, and let's just switch the alpha carbon so that iodide is a wedge and hydrogen is a dash. Okay, so now, and again, you'll get used to doing this without the Newman projection, but you can see that HA and I are no longer anti to each other in this particular conformation. We'll draw the carbon in the front with the benzene ring. HA is here, methyl is here. And the carbon in the back, iodide is here, proton is here, and the R group is there. So see now, oops, the leaving group and HA are not anti to each other. So I must instead rotate, let's go counterclockwise by 120 degrees, rotate the carbon in the front. That will bring the methyl group here, the R group here, HA here, where it is now anti to the leaving group. Now everything falls into place. When HA is anti to the leaving group, the two benzene rings are cis to each other, and this is going to give us 100% of our desired, product. So this is a good question because it makes you think very carefully about the requirements of the E2 reaction and getting the stereochemistry right. Go ahead.
Why did that one yield 100% over desired, but the other one with the cis isomer didn't?
This one up here didn't because there were two beta protons. If you removed HA, you got the desired one. If you removed HB, you got the undesired one. And this one being more stable than the desired one, you'd end up with a major amount of this and only a minor amount of that. Okay, so now we need to deal with something called regiochemistry or regioselectivity, which means selectivity among possible constitutional isomers. What we've dealt with so far has been stereoselectivity. That is, which stereoisomer do you get, cis versus trans? Now you're going to see that in some molecules you have to worry not only about stereochemistry but also multiple kinds of beta protons. So let me give you an example of this. Here is a leaving group, a secondary alkyl halide. We're going to use a good a good base that is also a weak nucleophile because of sterics. We'll just use the base DBU, which is one of our sterically hindered bases. We won't worry about what the structure of DBU looks like. Importantly, though, this secondary alkyl halide starting material has two different kinds of beta protons, beta carbons rather. You have orange beta carbon and blue beta carbon. And orange beta carbon is a methyl group. Is just a methyl group, and it's attached to 3 different hydrogens. And so we can relax a little bit in terms of stereochemical requirements of E2 when we're dealing with a methyl group, because these 3 protons are identical no matter which one is anti to the leaving group. If we remove it, we're going to get the same product. As it's currently drawn, the proton that is a dash is the one that's anti to the bromo leaving group. And if we remove that orange proton, we're going to get the following product, which is a monosubstituted alkene. We call it monosubstituted because of the carbons that are bonded to the alkene. Of the things bonded to the alkene carbons, only one is carbon, the rest are hydrogens. Now, on blue beta carbon, you have protons HA and HB. Currently, as drawn, HB is the one that is anti to the leaving group. If we remove proton HB, we get this trans disubstituted alkene. But as you know, we can rotate freely around carbon-carbon sigma bonds. And so we won't do this on paper, but we've gone through it before above, if we rotated around this bond, we could get HA to be anti to the leaving group, and that would give us the cis disubstituted product. So this is if we remove HB, this is if we remove HA. Now, of these products, what do we observe in terms of selectivity? Well, we're going to apply what's called the Zaitsev rule, which, as I said, is that the more stable alkene is the major product. And that be in the E2 reaction, that is because the more stable alkene forms faster, because the transition state leading to it is lower in energy. And then two basic principles of alkene stability are that more substituted alkenes are more stable. And second, that because of sterics, trans is more stable than cis. The explanation for why more substituted alkenes are more stable is the same explanation for why more substituted carbocations are more stable. It's hyperconjugation. And I will maybe illustrate that for you another time. Right now, I'll just summarize it's sigma to pi star hyperconjugation. So among these alkenes, the trans disubstituted is the more stable alkene, and so that you would expect that to be your major product. So how might this show up? I could ask a question of the possible elimination products for this reaction, which is the most stable? Or I could simply ask, of the possible elimination products for this reaction, which is the major product? And that's the same question. Yeah?
Could you, like, define disubstituted and monosubstituted? You said it's just the number.
Yeah, so look at the two atoms involved in the pi bond. They're each bonded to two other things aside from each other. So 4 possible, 1, 2, 3, 4 possible things attached to alkene carbons. If one of them is not hydrogen, we call that monosubstituted. If 2 of them are not hydrogen, we would call that disubstituted, and so on.
So I know you said that you don't have a process of naming HB and HA, but it seems like you put HB normally on the one that's the opposite of our leaving group.
That's purely, you said that I'm normally putting HB, the one opposite the leaving group. That's purely accidental. But the point is that the one that's going to get removed is the one that's anti to the leaving group in whatever conformation.
And whatever one anti is trans, and whichever one is.
Yes and no. So if you're talking about the proton in the beta proton in its relationship to the leaving group, the proton has to be anti to the leaving group in order for it to be removed. Now, when you're talking about trans versus cis, I think you're talking about the relationship between these benzene rings and the Newman projections. And yes, groups, once you've got the beta proton anti to the leaving group, other groups that are anti to each other will be trans to each other in the product. And once you've got the leaving group anti to the beta proton groups that are gauche to each other in that conformation will be cis to each other in the product. Yeah?
Would we ever have to compare a disubstituted, like cis versus a monosubstituted trans?
So you have to compare disubstituted cis versus monosubstituted trans? No, because if it's monosubstituted, there is no cis or trans. Yep. Okay. Let me give you another example of this, of sort of selectivity. Here is a starting material I think you've seen before for a different problem, but let's change the base now to be something that is a weak nucleophile but a good base, and so E2 is our reaction outcome. We've got two different kinds of beta protons, beta carbons here. There's orange beta carbon and blue beta carbon. The proton on orange beta carbon that would be reactive is the one that can be trans to the leaving group, which is in this case chloro. And then the proton on blue beta carbon that could possibly be trans to the leaving group is HB. Notice that I didn't draw as reactive the protons that are on the same side of the molecule as chloro. And the reason here is that unlike the systems we've dealt with above, because this leaving group is in a ring, you can rotate a little bit, but not completely freely around the bonds between the alpha and the beta carbons. There's no way to rotate around the bond between orange beta and alpha to get this wedge proton to be a dash. You can't do that without breaking the ring. So in a ring, if the leaving group's in a ring and you have beta protons in the ring, only those beta protons that are anti or trans to the, only those beta protons that are trans to the leaving group can possibly be anti to the leaving group. Now, if we remove the orange one, we're going to get this product which I will draw in orange. If we remove the blue one, we're going to get this product that I will draw in blue. Notice that they are both disubstituted alkenes, meaning two of the things attached to the alkene carbons are, only two are carbon, the other two are hydrogen. So these are both products. I wouldn't require you to say which one was major or minor. And they are, the relationship between these two products is they are regioisomers. That means constitutional isomers. They have different connectivity. All right, I want to do two more examples. The one's probably going to take most of the time, and the other one we'll have to get to at the beginning of next time. And this one is better done in sort of a explain it after the fact rather than predict what would happen. This is actually a problem that's in your one of your problem sets. I don't know whether it's problem set 7 or the alternative problem set 7. But you've got this interesting fused 6-membered ring system. There are 6 atoms in this ring, and then 2 atoms shared between 2 rings, 10 atoms in the ring system overall if you don't count the substituents. This is called a transdecalin. And I'm going to add a few other substituents to the transdecalin. One is a methyl group here pointing up, and the other is a bromo here pointing down. I'm going to draw the chair conformation of the transdecalin, and it turns out there is only one possible chair conformation for the transdecalin, and it's the one I'm drawing for you right now. This methyl group is upaxial on an up carbon. This wedge methyl, or a dash methyl group, is down equatorial on a down carbon. And then bromo is going to be down equatorial, and methyl here is going to be up axial. And it turns out that this transdecalin is what we're going to call conformationally locked. By that we mean there is only one possible chair. Now for most 6-membered rings, there's 2 chairs. There's the chair and the other chair. Go ahead.
Is a fused ring always going to be conformationally locked? Because there was one on, I think it was problem set 5, that there were I could only figure out one of them. So it's consistent.
The one on problem set 5, I believe, was also a transdecalin. We won't talk about it today because it's not important really for what we're going to say. But cisdecalins exist, and cisdecalins are not conformationally locked. But that's sort of a topic for another time.
Were they both on the exam today?
No, elimination's not on the exam, which I think you all knew. Yeah. Let's see. So, why is the transdecalin conformationally locked? If you think about it from the perspective of this ring A here, for ring A, this carbon is at an up position, at a peak position. This carbon is at a valley position. The methyl group here is up axial. The methyl group here is down equatorial. And importantly, these two ring groups, one is down equatorial, the other is up equatorial. If you tried to flip, yeah, go ahead.
Why is it down equatorial?
Why is what down equatorial?
The methyl group on the down.
Did I say equatorial? I meant axial.
Okay, cool.
Sorry.
No, you're good.
If I tried to go to the other chair for carbon A, that would involve up carbons going down and down carbons going up. That would involve axial methyl groups becoming equatorial. And importantly, that would involve this axial ring group, which is up equatorial, becoming up axial, and the other one, which is down equatorial, becoming down axial. Now, the reason that can't happen is because those two atoms in gray are tethered together by two other atoms, and it literally can't stretch. If that may be hard for you to visualize, you'd have to build a model to really see it. If you build a transdecalin and try to flip the chair, you end up breaking the model because it simply can't stretch that far, okay? So here's why this is important. If you don't look at the conformation, but instead just look at the molecule from above, you would recognize 3 possible beta protons here. 3 possible beta carbons. And you would say, okay, well, there's a proton here that's at an up position that can be that is trans to the leaving group in green. Sorry. Then on the other carbon, on the orange beta carbon, you could identify a proton that is trans to the bromo. And then beta carbon, the pink beta carbon is a methyl group, and there are 3 protons on that carbon, and if we rotate around that methyl group, surely we can get one of those protons to be anti to the leaving group. So you might anticipate that you would see 3 possible products for this reaction. Instead, if you were to use a good base that's a bad nucleophile, you only observe the pink product, the product from removal of a pink proton, and you do not observe removal of the blue proton or of the orange proton. Let me show you why that's the case. As I said, this is the transdecalin conformation. If we draw the blue proton that's trans to the leaving group, it's at an up equatorial position. If we draw the orange proton that is trans to the leaving group, it is also at an up equatorial position. Now, what's the problem with that? What's the relationship between the orange proton and the leaving group? Are they anti to each other or are they gauche? Yeah, stuck because it's conformationally locked in a gauche position, not anti to the leaving group, and therefore not reactive in an E2 reaction. Same thing with the blue proton. It's gauche to the leaving group, not anti to the leaving group, and so not reactive in an E2 reaction. In fact, it's only this adjacent methyl group that can rotate its protons such that one of them can spin around to be anti to the leaving group. In this conformation, it's this proton that is anti to the leaving group. And so it's only that proton that gets removed. So that is perhaps the hardest case of dealing with the requirement that protons be anti to leaving groups. Yes?
Those other two beta carbons, the blue and the orange, do they not have another proton?
They do, but that proton is also not anti. It's also gauche to the leaving group.
Why would we?
I actually don't know that I could answer why aren't they anti. I can only illustrate that they are not. So I'm drawing you the Newman projection of the orange carbon in the front. And then here's the methyl group in the back. Here's the bromo, and here's the other ring carbon in the back. So this is the one in the ring that's trans to the leaving group. This is the one that's cis to the leaving group, but they're both gauche to the leaving group. Yeah. Yes?
So for the leading group, if it's in a ring, it has to be axial. There'd be for a beta
So,
shape in the ring as well.
if you're in a six-membered ring, the beta proton and the leaving group both need to be axial. Now, normally that's no problem because you can always flip to the other chair, right? It is a problem here because you can't flip to the other chair. Okay. The last thing that we need to do, and I think we'll just have time to set this up, is to deal with a reaction where E1 is a possibility when there is also resonance. So imagine taking this secondary alkyl halide with a molecule that is a weak nucleophile and a weak base. The water is not going to attack first. It's got to wait for the leaving group to leave. So you're going to get both SN1 and E1 products. When the leaving group leaves, you get this carbocation that, as we talked about last time, is resonance stabilized. And I taught you how to draw the products that would come from the SN1 reaction of water as a nucleophile. But now you need to also deal with the E1 products. To deal with the E1 products, you're going to need to consider protons that are beta to the positive charge and that can line up with the empty p orbital that is the LUMO. And we will deal with that more next time. So, good luck on your exam, and I will see you Friday.